సౌజన్య మేడం.
Sir, she's joining, sir.
ఓకే రైట్. నిన్న గ్రూప్లో కూడా పెట్టాను ఆ సార్ది బయోడేటా. ఒకవేళ ఆమె కాకపోతే మీరు తీసేసుకోండి.
Okay, sir. Okay, sir. No problem.
Sai, have you checked the audio? Session 2 poster. Welcome slide. Who is the technical person today? Please respond immediately. Thank you, Naresh sir.
Thank you, sir.
Very good morning to all the participants and welcome to the day 2. And he's going to join, speaker can join in another 2 to 3 minutes. So some login issues he is facing at the university. So he'll join in 2 to 3 minutes. Please bear the delay.
Good morning, sir. Am I audible?
Sir, good morning, Malaya Kumar Nath, sir.
Good morning, sir. Yes, yes.
Right, sir.
Good morning, sir.
Are you ready, sir? Shall we
Good
start,
morning,
sir?
Yes, yes, madam. Yes, sir. I will start. Yeah.
All right, hand over to Jaya, please.
Welcome to one and all present here. It's my great privilege to introduce today's speaker, Dr. Malaya Kumar Nath, sir. Dr. Malaya Kumar Nath, sir, has completed BE in Electronics and Telecommunication Engineering from BPUT, Odisha in 2003 and MTech in Electronics and Communication Engineering from IIT, Guwahati, India in 2008. He has completed his PhD from IIT, Guwahati on signal processing. Now he is working as an assistant professor in the Department of ECE, NIT Puducherry, Karaikal, India since July 2013. He was seconded to Asian Institute of Technology, Bangkok, Thailand by President of India for teaching error control coding in the year 2018 for 1 semester. His area of research is machine learning and image processing. He has 25 publications in reputed SCI journals and international conferences. He has 2 funded projects. So thank you, sir. Thank you for being with us. Now I request and welcome Dr. Malaya Kumar Nath, sir. Please take over the session.
Thank you, ma'am. Thanks for the brief introduction. I welcome you all. Good morning to all the participants. So can I share my screen?
Yes, sir.
How to share, madam?
Sir.
Just this arrow I have to press. Yeah.
Yes, sir. Arrow icon is there, sir.
Yeah. Complete desktop. Yeah. Is my screen is visible to you, madam?
Yes, sir.
Yes, sir.
Yeah. Okay. Once again, good morning to all. Today, we are going to discuss about fuzzy set-based neural network, its applications. So, under this category, basically, I will discuss what is this fuzzy set, how this fuzzy set will helpful for this ancient world, that how to handle a huge amount of data in terms of the neural network. Basically, when the neural network has been started, it was started with a single layer neural network, and it has a large number of limitations or disadvantages. And these disadvantages can overcome by introducing more and more layers into the network. And basically, this will give rise to a deep neural network architecture. Basically, this neural network, deep neural network, artificial intelligence, all these mimicking our human brain. So we are talking about deep neural network, and recently people have worked on neurocomputing, which is also again a similar kind of actions that is taking place as our brain. That means it is mimicking our human brain for better computation and faster computations with a lesser power. So we'll talk about neuromorphic computing. Also, we'll talk about how this neural network optimization is done, so that we can able to get the solution of that. And at the end, we'll talk about some of the applications as well as how this is hardware basically developed, what is the architecture people are using for this neural network, neural networks or different type of neural networks. So this is my plan of talk. Already I have talked about that. I will talk first about fuzzy. Then I will go about this artificial intelligence, machine learning, as well as how this machine learning has been evolved. That we'll talk about. Then I will talk about this optimization, so how this optimization is occurring by the help of machine learning and neural network, that is neuromorphic computing. Basically, this neuromorphic computing is a newer concept which is basically mimicking our human brain. So it mainly focusing about huge computations as well as the lesser power. So if we look into the fuzzy sets, that means in this introduction part, we'll talk about what is fuzzy set, what is a soft set, and how this is helpful in the perspective of machine learning. So according to Leo, proof that the every fuzzy set on an universe U can be considered as a soft set. So basically, this artificial intelligence deals with a large amount of data. So dealing with big data by classical methods is not always successful because of various types of uncertainties which is present. So what are the uncertainties present in the data? If we look into the uncertainties present in the data, so we can see the fuzziness, randomness, roughness, ambiguity, inaccuracy, incompleteness. These are some of the uncertainties which is associated with the data. So mathematical tools basically used to analyze or deal with these uncertainties are not about two things. One is called the fuzzy set, another is called the soft set. So this fuzzy set was developed by or introduced by Dept, and the soft set theory was introduced by Malaya. So these fuzzy sets as well as soft sets are very useful in many kind of applications like decision making, data mining, business, social choice, forecasting, clinical diagnostics, etc. So if we look into the fuzzy set, how this fuzzy set can be represented by. So according to Malaya, he pointed that this fuzzy set is nothing but a specially kind of soft set, and this fuzzy set was initially introduced or proposed by Dept in 1965. This fuzzy set represents a mathematical method for describing the fuzzy phenomena in mathematics. What is that fuzzy phenomena? According to the definition given by Dept in 1965, so let U be a set and called as the universe. So U is the universal set, and a fuzzy set mu on U is defined as a membership function, so that this mu can be represented as U that is from range between 0 to 1. So for any x which is belonging to U, the value of mu x represents the extent to which x belongs to a fuzzy set of mu. So in mathematically, it can be represented as the fuzzy set mu that is equal to mu is equal to x mu x, such that this x is belonging to the universal set. So this fuzzy set can be either discrete or it can be continuous. So this discrete fuzzy set can also be expressed as that is equal to mu x I is equal to 1 to n mu of xi divided by xi, where n belonging to the number of elements present in the universal set that is equal to u. So if we'll see the fuzzy set, different type of operations that is possible according to Dept. So the maximum, minimal operations proposed by Dept that is equal to intersection, union, complement of fuzzy sets are defined. So this is called the intersection, so union as well as the complement. So the intersection can be represented as mu x, intersection of Vx that is equal to mu x, union of Vx, complement 1 minus mu x. What is soft set? This is soft sets and induced soft sets. This is introduced by Mulder. So let U be a universal set and E be the set of possible parameters under the consideration with respect to U. So usually these parameters are attributes, characteristics, or the properties of any object. So we can define that is equal to U, E will be called the soft set or soft set. So let us consider PU denote the set of all subset of U, and Mulder's denoted the notion of soft set in the following way. So the way he has developed, that is a pair, that is F, A is called a subset over U if when A is a subset of E and F is a mapping function which is given by that is equal to A to P of U. So that means this is soft set over U is a parameterized family of subset of U, and A is called the parameter set of the subset F, A, where E belongs to A. So F of E may be considered as a set of E approximate element of F, A. So now, how this neuron-based subset as well as fuzzy set can be utilized? So basically, in case of a practical application, we are dealing with a huge amount of data. So the practical applications, these fuzzy sets and subsets are often used as an independent tool to solve some practical problems. So what are the current difficulties that we are facing with the fuzzy sets? So the current difficulties are when the fuzzy sets are used to solve practical problems in the construction of a membership function, it is difficult and sometimes it is very, very subjective in nature. So that means this membership function is depending upon person to person. So when using a subset to solve the practical problems, it usually has a large amount of data, because today the world is full of data. We are getting so many sensor data, so many information in the form of a data we are collecting. So, and the essential characteristics behind the data are not revealed. So that means all operations are based on original data, and this usually not a good idea under a big data conditions. So idea of using the soft fuzzy, that is a soft fuzzy artificial neural network model to solve the problems similar to that of the neural network problems. Basically, this neural network is used for many kind of applications, starting from segmentation to classifications. So similarly, the soft fuzzy artificial neural network model solve many kind of problems. So an induced soft set can be represented as a set of points in an n-dimensional space. Training the soft set by using a neural network, we can construct a fuzzy set that is equal to X. And from the perspective of the classification, it is actually, basically, we are finding a curve or a surface or a hyperplane such that the data which are present in a different dimensional space can be segregated or can be separated. So for a new sample T, it indicates the extent to which T belongs to the category. So that means what exactly we are doing in this case, we are basically finding a hyperplane or a straight line so that the different groups can be classified. After that, we can put into a new sample that is represented by T. And we are basically finding what extent it is belonging to which category. So this is soft fuzzy artificial neural network has many advantages. Some of the advantages have been noted down here. So it can be used as a general method to construct the membership function of the fuzzy set. It reveals the relationship between the ambiguity and the accuracy and provides a new perspective relationship between fuzzy set and subset. It provides a further reference for the application of subset and fuzzy set in an artificial intelligence. So the construction of this fuzzy set from the subset, this can be proposed by this modal logic algorithm. So what is this modal logic? So in this case, we are considering W is equal to W1 up to Wn, which represents n possible states of world or simply state with respect to W. A Dept concept is represented by n trip set that will be represented by A is equal to A W1 up to AWN, where Wi are described by the trip set that is equal to AWI. So in this case, we can define a U that is a universal set, be a finite non-empty set that is called universe. And all set families of n trip sets is given by the n-fold Cartesian product that will be represented by the product of n, that is 2U, that is equal to 2U cross 2U up to 2U. And suppose this omega, which is represented, that is W 0 to 1, is a weighting function satisfying the conditions. And if we are assuming that the summation of I is equal to 1 to n, Wi is equal to 1. So for this element, this product terms n un representing a Dept concept, and which is proposed by a fuzzy set model, and that can be fuzzy set model can be represented as that is equal to mu a x summation I is equal to 1 to n Wi mu of a Wi x. So what is this mu a or mu a Wi x? This mu a Wi x is representing the characteristic function of this a Wi. And if each trip set a Wi represents one view of the Dept concept, the fuzzy set may be interpreted as a weighted combined view. So how this weighted combined view can be represented? So now this is the concept. So that is equal to, we are taking this input. These are nothing but the subsets, and this will be associated with a weight that is equal to W1, W2, W3 up to Wk. And this is the aggregation, that is the fuzzy sets. So the construction of fuzzy set based on some aggregation operations is represented here. So what is this mu x? Mu x is equal to nothing but W1, U1 plus W2, U2, all the summations as for this equation. That is equal to Wi a mu a Wi x. So now it will represent in the form of a perceptron. So now these are my inputs, that is equal to E1, E2 up to Ek. And these are my weights, that is equal to W11, W1 to W up to 1K. So and this will be add up at a neuron that is equal to by the help of a summation, and it is associated with a bias term that is equal to B. And this summation that is equal to, I can say this output is equal to some W transpose X or W transpose E plus bias that is equal to B. And this is passed into the activation function. And based on the output of the activation function, the neuron is fire or not to fire. So this is the simplest perceptron. We'll talk about more in detail. So now, so how this fuzzy set can be used in the form of a neural network. And this basically done by the help of a learning concept. So now, sorry. So now what we have done, what we have discussed here is that this fuzzy set can be used for handling a huge amount of data. So, and this can be represented in the form of a neural network representations. And this neural network, whenever we are talking about a neural network representations, basically we are mimicking our human brain. That means the way human brain is functioning, the way human brain is computing, the same way we are trying to transmit the output from the one set or one or input side to the output side. So this will give rise to the different concepts. One is called the artificial intelligence, neural network, neuromorphic computing. So now So what is this artificial intelligence? So this artificial intelligence represents the computers could able to think, or the computers can make to think. So basically, this is an idea or an effort to automate the intellectual tasks performed by the human by the help of some machines or robots. So now how it can be possible? It can be possible by the help of the neural network. This neural network is nothing but the interconnection of networks or interconnection of small processing units that is known as the artificial neurons. And basically these artificial neurons are mimicking our human brains. So next concept is coming, that is called your neuromorphic computing. Basically this is inspired by the biology and implement the theory of human brain modeling, that is the neurons and synapse. So how these neurons and synapse are working, basically this is done by the help of neuromorphic computing, and neuromorphic systems provide a unique and a novel solution for this artificial intelligence. So now, as we have discussed the three concepts, very important concept, AI, neural network, and neuromorphic computing, maybe within 2-3 years, people will be talking about only neuromorphic computing. They will not talk about this neural network or deep neural network or the machine learning. So now, what is this learning? So we will try to understand that how basically this is evolved and how the different problems can be overcome at different stages. So if we look into the learning is nothing but the machines can able to think like human beings. So according to Ambrose in 2010, this learning represents a process that leads to change, which occurs as a result of experience and increases the potential for improved performance and future learning. So that means whenever one task is performed with respect to some experience, each time the task or the performance has to be improved. So if we look into this machine learning, basically this machine learning represents the story of algorithm that improve the performance at some task. And how it can be possible? It can be possible by two ways. One is called the use of statistics, and another by using the computers. So if we look into the machine learning related fields, basically these different fields have been coined by by the different researchers. So these different disciplines of machine learning are artificial intelligence, neurobiology, data mining, probability statistics, numerical optimizations, etc., etc. So there are varieties of machine learning concepts are present. So the varieties of machine learning have been represented here. That is, a few of them are clustering algorithms, genetic algorithms, and so on. So now we'll talk about how this machine learning is basically working. So this, as I already told, this machine learning can able to learn from the data. That means from the experience. So the computer program can able to learn from the experience with respect to a task, such that this performance has to improve into the experience. That means each time the performance has to be improving. So now we'll take one example. Suppose a robot able to walk. So in this case, the walking is nothing but a task, and how to program a robot is nothing but actually the learning process or the learning. Now we'll talk about what is the experience. These experiences are coming from the databases. One of the popular database that is nothing but the AICTE database, and this AICTE database was developed by Fisher in 1936, and he has taken 150 different AICTE plans, and these 150 different AICTE plans are separated based on the sepal length, sepal width, petal length, as well as petal width. So now, if we look into the experience, then the machine learning algorithm can be mainly classified into supervised, unsupervised, as well as reinforcement learning. Again, this unsupervised learning is divided into semi-supervised, self-supervised learning, etc. So now, what is this supervised learning? So basically, in case of supervised learning, we are mapping the input data to a known target. That means there is some annotation is present. So in this case, it involves observing of several examples of a random vector S and an associated value of vector Y. So that means learning to predict Y from S. That is equal to, we are basically estimating the probability of Y for a given input vector that is equal to X. So this type of supervised learning is very popular in case of optical character recognition, speech recognition, image classification, language translation, etc. So if we take one very famous example of this supervised learning, that is equal to nothing but how the child and parent relationship. When during our childhood, basically a child or during the childish period or during the childhood, whatever the task is performed by the child, basically this is given by, or the result or whatever the result will be decided by the parent. So basically, before performing any task, we know what exactly will be the result. Or in this case, the annotation is basically present. On supervised learning, in this case, there is no annotation is present. There is it is basically a type of learning without the help of a target. So in this case, we are observing the different instances of random vector x and aiming to learn the probability of a distribution that is equal to P of x. So basically, this type of algorithm is used for clustering, dimensionality reductions, as in case of a principal component analysis, etc. So now, if we take one example, real life example, that how a adult people basically behave. Basically, he doesn't require any result, any annotation he doesn't require. Based on this input feature vector, it is taking one decision. So next is called the self-supervised learning. In this case, this is a kind of supervised learning without any without human annotated labels, but still labels are involved, but generated by the help of some heuristic algorithm. One of the particular example is called the autoencoders. So basically, this is self-supervised learning. Another example is nothing but suppose whatever the next frame is coming in case of a video sequencing, that can be predicted from the past samples or past frames. When we are typing something in our Gmail, what will be the next word that can be predicted by the word that we are typed previously. So that means this is a kind of self-supervised learning, which is producing some annotations based on some heuristic criteria. So this is called the self-supervised learning. What is semi-supervised learning? In case of semi-supervised learning, a portion of these labeled examples are used, and this portion of these labeled examples are used to generate a huge amount of labeled examples or labels. So basically, this generative adversarial network, this is particularly used for generating a huge amount of labeled data from a small portion of this labeled data. So if we compare this self-supervised learning as well as the semi-supervised learning, then we can find some similarities between this self and semi-supervised. So this self and semi-supervised, both of these learning techniques do not entirely depend upon the manually labeled data. If we look into the self-supervised learning, it depends on the underlying structure of the data to predict the outcomes. It involves no labeled data. Basically, one of the examples is the autoencoders. Semi-supervised learnings are nothing but a small amount of labeled data is present or used. So one of the example is nothing but a generative adversarial network. So next type of learning is coming into picture, that is called the reinforcement learning. So basically, this kind of learning don't experience any kind of fixed data sets. So how exactly it is working? Basically, it is consist of one environment as well as an agent. So it will be working on the principle of a feedback concept. So the agent is taking the feedback from the environment. So based on the feedback, the agent has to perform a task in such a manner that the reward is get maximized. One of the popular example is our how a person is behaving during his professional life. So during our professional life, basically we are performing the task by looking into the surroundings in such a manner that everybody will praise to us, or our higher authority will be happy on us. So basically, this is working on the principle of a feedback concept, as well as it doesn't work on any kind of a fixed database. It looks into the surroundings, it looks into the environment, and from the environment it is taking a feedback, and based on the feedback, it has to perform the task. One of the another example is how a self-driving car is working. Basically, the self-driving car is moving ahead, or it has to take a left turn or a right turn, or it has to stop into the near the signal, or it has to increase the speed or decrease the speed. Basically, it depends upon the surrounding condition or the condition of the road. So next is called the transfer learning. So basically it uses a transfer of knowledge from the related task that has been already pre-trained. This improves the learning process and useful for very reduced amount of databases. And basically, in this case, the CNN, that is convolutional neural network, which is basically working on a huge amount of data set, is used. So these are the experiences that we have discussed, different kinds of learning. So here I have summarized the different learning. If we look into the traditional programming, we have some set of rules and data. Basically, from the rules and data, we are finding certain answers out of that. In case of supervised learning, we have some set of answers and data, and from the answers and data, we are basically finding some set of rules. In case of unsupervised learning, the data is known to us. There is no answer is given to us. So from the data, from the probability of the distributions, we are finding some certain set of rules. And in case of reinforcement learning, basically one environment is present, one agent is present, and basically there is a feedback from the environment to the agent. And based on the feedback, this agent is performing a task or an action such that the reward is get maximized. So these are the different types of learning that we have discussed. So if we see, it is a different type of machine learning learning that are used for various kinds of applications. If we look into the supervised learning, basically it is used for classification as well as the regression tasks, whereas unsupervised learning is used for dimensionality reduction, clustering, density estimation, etc. So if we look into these different tasks performed by the supervised learning as well as unsupervised learning, they can be performed by the different techniques or methods, and few of these methods have been noted down here. Similarly, this reinforcement learning is performed by the deep Q network, double Q learning, prioritized experience replay, etc. So these kind of machine learning have been used for different types of applications, and some of them have been noted down here. So you can get the details about this in this reference paper. So what we have discussed the different type of learning concepts. So supervised, unsupervised, self-supervised, semi-supervised, reinforcement learning, as well as the transfer learning. So if we look into the supervised learning, this supervised learning is performing two types of tasks. One is called the classification, another is called the regression task. In case of classification, we are classifying the output into different groups. And in case of regression task, basically this is a problem of predicting a continuous quantity output for a given example. So when we are performing either the classification or the regression task, basically we are facing a challenge that the algorithm should perform well to the new unobserved inputs. That means the network or the model should perform well to the unobserved or unseen or the new inputs. So basically, this will give rise to an error that is known as the generalization error, and the generalization error has to be minimized. So basically, this is the challenge that we are facing in case of supervised learning. If we look into the learning algorithms, these learning algorithms have been implemented in a neuromorphic hardware. Work has focused on spice-based learning rules as well as non-spice-based ones. So these non-spice-based ones are basically represent to the LMS, perceptron, etc. And how this perceptron is converted into a deep neural network that we are going to look at here. So in case of LMS and perceptron, basically they will train the single neural network. So both this LMS algorithm as well as perceptron follow the minimum disturbance principle. What is this minimum disturbance principle? This minimum disturbance principle says that what is the error is coming, and that error has to be minimized. That means we have to correct the error at each and every step by minimal change of the parameters and to maximize the memory capacity. So this LMS algorithm is implemented basically on adaptive surface like exclusive for filters. So if we look into the perceptron, this perceptron is a non-linear network by adding a threshold function on the output of a adaptive linear combiner, that is ADA-line. So what is this perceptron? Basically, perceptron is nothing but a non-linearly separable, that means it can a neural network which can able to separate the linearly separable classes, but it cannot able to separate non-linearly separable classes. So that means this perceptron has a disadvantage that it doesn't guarantee low classification error for non-linearly separable classes. That means these non-linearly separable classes cannot be separated by the help of the perceptron. The back propagation after this perceptron, this back propagation and gradient descent has been the popular learning algorithm for training both shallow as well as the DNN in the few decades back. Basically, this back propagation and gradient is used to calculate the weight. So the weights are adjusted in such a manner that the error has to be minimized. Sorry. So the issues that is present with this back propagation, that it is costly both in terms of memory and as well as the power due to high precision weight. It has a smooth activation functions like tan hyperbolic x, sigmoid, etc. Significant number of multiply as well as accumulate operations for both forward as well as backward passes are present. This back propagation requires a global information about the error, well at the weight of backward pass that are exactly symmetric. So that means this weight matrix in the back propagation, that is forward pass as well as backward pass, has to be symmetric. Weight transport problem, which is analog with the alternating forward and backward passes, and precise floating point weight make a standard back propagation and implausible learning technique for neuromorphic architecture. Computational complexity and optimize the memory resources problem in case of back propagation can be removed by a pipeline back propagation algorithm and a binary state network. So the pipeline back propagation network has access to the previous network states and helps delay gate of text during the subsequent forward pass without the need for an explicit backward pass. The architecture reduces the number of memory pages and the lookups, the corresponding to the backward pass significantly. So reduction of redundant off-chip memory pages reduces the power overhead appreciably in case of this backward and forward pass. So this is nothing but the binary state network in which the output of the neural network can be either 0 or 1 in case of unipolar, and in case of bipolar, which will be either -1 or +1. So this will talk about in terms of neuromorphic computing. This is timing dependent plasticity as well as spike driven synaptic plasticity will talk in case of neuromorphic computing. So we have discussed that the two tasks we are performing in case of supervised learning, that is called the classification as well as the regression. And our main aim is to the data, the network should perform well to the on-scene data or on-object data. So our aim is to always minimize the generalization error that we have learned from here. Now we will see how this generalization error can be minimized. The generalization error can be minimized by minimizing certain error criteria. And that error criteria is nothing but we are performing some optimization. So we'll see how this optimization is performed.
Hello, sir. Sir, your voice is not audible.
Some of you made him as an attendee.
So, dear technical team, please look into this issue.
So please unmute yourself, sir.
Sir, it was already on how it becomes mute, I don't know. Sorry for the inconvenience. Yeah.
Audible, sir. It's audible now.
Yeah, sure. Yeah. From which slide it was not audible. Can you tell me so that I'll just quickly review that point?
Just one slide, that's it.
Okay, okay, fine. Yeah. So what we are discussing that in case of supervised learning, we are talking about two tasks. One is called the classification, another is called the regressions. So in case of regressions, basically the goal is to build a system that can take a vector x as the input and it will predict the value of the scalar y as the output. So our aim is to predict the output value that is equal to y hat, that is equal to wtx. And what is this w basically represent? This w represents a set of weights which determine how each feature vector basically predicts or feature vector affects the prediction. So what will happen if w will become positive? If w will become positive, it will increase the prediction as the input feature vector increases. If w will become negative, then it will increase the prediction if the feature vector x decreases. So if w is equal to 0, there is no prediction. So now what we have done, we have found the predicted value that is equal to y hat is equal to wtx. What is our aim? Our aim is to make this y hat is almost equal to y. So how we can make this y hat is equal to y? So for that reason, we have to calculate the mean square error that can be computed as 1 by n summation I y hat test minus y test whole square. And if this error is minimized, if this error is very, very low, then what will happen? Or I can say this MSE is equal to 0, then this y hat will become equal to y. So our aim is to minimize this MSE, or we have to make this MSE to be very, very low. So how we can make this MSE to be very, very low? So for that reason, we have to calculate the gradient of this MSE with respect to w, because in this case, the input feature vector is known to us. So the prediction is basically depending upon the weight vector that is equal to w. So if we calculate the gradient that is of MSE with respect to w and equate to 0, we can get what will be the value of this w such that this MSE will be minimum. And this is called the simplest learning algorithm. Here I have taken one example of that 10 data points. It contains only one feature vector. Now I have to find a straight line in such a manner that the sum of the distances from all the points to this line will be equal to minimum. So this is nothing but a regression problem. So in this case, I have to find the weight vector that is equal to w1 in such a manner that it can represent a straight line passing through all the data points. So for that reason, I have to calculate for each value of w what will be the error or the mean square error. So the value of w where the mean square error will be very, very low, I can say that is my optimized or optimum value of w. And this is known as the optimization technique. So we'll talk about the different optimization techniques that people are using or the researchers are using in the literature for optimization techniques. So in this case, in case of linear regression, we are calculating y hat is equal to wtx. Sometimes this y can be represented as wtx plus b, where this b is representing a bias term. And basically this bias term represents how far this straight line is far away from this origin. So we'll talk about more in detail about this bias term. So when we are talking about this linear regression, the linear regression problem will lead to either the model to be overfitting, or it will make the model to be underfitting, or it will make the model to work in a proper capacity. So what is this different terms, that is overfitting, underfitting, as well as proper capacity? Basically, our aim is to make the training error to be very, very low, and our aim is to make this testing error to be also very, very low. So how to make this training error and testing error to be very, very low, or the to be low? So for that reason, we have to use an assumption that the data which is used for our training process is nothing but independent as well as identically distributed, that is IID. So our aim is to make our training error to be very small, that is equal to too low, and the test error, that is known as the generalization error, or also to be small, and the gap between the training error as well as the test error to be also small. So this will lead to the different conditions like underfitting, overfitting, as well as the critical fit. So what is underfitting condition? Underfitting condition is a condition where the model will not provide sufficiently low error at the training set. And overfitting is a condition where the gap between the and training error as well as the test error is exceeds a certain threshold, or it will be too high. So capacity of a model basically represents the ability of a model to fit a wide variety of functions, and it makes the model to either to be overfit or to the model to be underfit. So here three examples. One example is given and represented by three figures representing to the different conditions, that is called underfitting, overfitting, as well as appropriate capacity. In case of underfitting, we cannot get the sufficiently low sum of the distances when we are fitting the line with the data points. That means, in other words, I can say that the training error is too high in this case. That means, in other words, I can say that the straight line or the hyperplane cannot able to fit all the data points. In case of overfitting condition, basically this model can memorize the values of these feature vectors, or the memorize the property of the training set. In this case, the gap between the training error as well as the test error increases beyond a threshold. That means it will be too high. And in case of appropriate capacity, it can able to fit all the data points, and the gap between the training error and test error is also low. Training error is also low, as well as the test error is also low. Now we can see this by the help of an example. So here, the training error and test error is represented by the help of the blue line represents the training error and the green line represents the generalization error. If we look into the left-hand side of this curve, this is known as the underfitting zone. In case of underfitting zone, the training error is not sufficiently low. And if we look into the right-hand side, we can see that the gap between the training error as well as the test error is extremely high. And at this center position, I can say this red line point, the gap between the training error and test error is equal to low, as well as the training error is sufficiently low, and the test error is also sufficiently low. So this is called the overfitting zone. So these are the three different zones that we have discussed in case of this regression model. So this relation basically between the capacity as well as the error. So we have discussed what we have discussed. We have summarized that what is this learning and what are the different kind of experiences that we are facing, and we have seen with respect to one example that is called the linear regression. So what basically this overfitting, underfitting, as well as critical fit basically represents. So this we are talking with respect to the neural network. So basically we are talking about how the machine can able to think like the human being. So that means this represents to another domain of engineering that is known as the artificial intelligence. And this artificial intelligence, the main concept is the neural network. So that means the neurons are interconnected in such a manner similar to that of our human brain. That means it can loosely mimic the actions found in the human brain. We can directly go to the electrical representation of this neural network, in which there are certain set of inputs represented by x0 to xn, and each input is associated with certain weights that is equal to w0 to wn. If we assume this w0 is the bias term, then all these x0 w all the input into which the input with the weights will be multiplied and summed up at this location, that is the neuron or the soma or the cell body, and this will give rise to an output that is equal to y is equal to wtx plus b, and this will pass into an activation function that is equal to activation function. And if we are getting some output, then the next the neuron will fire. If it is below the threshold, the neuron will not fire. So this is the electrical equivalent of the neural network. So now we'll see how this neural network, which is nothing but a simplest model, consists of a single input layer and one output layer, can be converted into the deep neural network. What is the reason behind that? Why this simplest neural network is converted into a deep neural network? So we'll look into the history, then we can understand what are the disadvantages basically people have faced during the different stages of the neural network, so that this will give him to a deep neural network concept. So this, if we look into the history, the birth of this neural network, in 1943, Mark and Spitzer designed this fast neural network. This fast neural network is nothing but a simple unit that combined to give rise to increased computational power and the idea of the threshold. In 1939, Hopf developed the fast learning rule. So this represents if two neurons active at the same time, the strength between them should be increased. During the 50 and 60, the perceptron was developed. During the year 1969, there was a death of the neural network. And in the year of 1990, Bhatnik and Cox developed the support vector machine. So this is a popular neural network which can able to separate non-linearly separable problems. Artificial neural networks are renamed as this deep learning when Geoffrey Hinton and others introduced the idea of this unsupervised pre-training deep belief network, ReLU activation function, etc. So if you look into the evolution of this artificial neural network, in 1943, Marklock and Walter Spitz developed this binary threshold of the neuron. In 1957, Frank Roosevelt invented the perceptron as well as the famous perceptron loop. In 1960, Minsky and Puppet showed the limitation of the perceptron. There was a winter break during this period, and in 1980, Geoffrey Hinton David revived this artificial neural network by using the back propagation for the multi-layer perceptron network. In 1990, the support vector machine was developed. In 2000, this ANN was renamed as deep learning. In 2010, ImageNet is coming into picture, and 2012, this Alex Illa and Geoffrey Hinton owned this ImageNet computation by using this deep learning with a huge margin dropout regularization and the ReLU activation. So this is the evolution of this artificial neural network. Now we'll see the simplest perceptron and how this perceptron has certain limitations and how these limitations can be overcome by using a multi-layer neural network. And if we are using a deep neural network, then what will be the advantages that we are going to see? We can see these things here. So now we'll see the simplest perceptron. The simplest perceptron is nothing but the perceptron is nothing but the linear binary classifier that uses a hyperplane to separate two classes. In the figure, I have represented two classes. One class is represented by the plus side, another class is represented by the negative side. So the two classes can be separated by the help of a hyperplane that is equal to AB. If I can say this WTX plus D is greater than 0, that is corresponding to the positive class, and WTX plus D that is less than 0, that is corresponding to the negative class. And what is this W? This W is nothing but the weights which is deciding the hyperplane. And B basically represents the bias term, which basically represents how far this hyperplane is from the origin. So now we'll try to understand this perceptron by the help of a simplest example. Everybody, we all know that is a two-input logical OR gate. We know that in case of a two-input logical OR gate, the output is equal to 0 if and only if this both the inputs are equal to 0. If one of the input is equal to 1, the output is equal to 1. So now my aim is to make a model in such a manner that the output of a two-input logical OR gate can be separated. So that means 0, 0 input will give rise to 0, and all other combination of the input is giving rise to 1. So now, if I represent this input-output combination by the help of a graphical representation, by taking the x1 and the x-axis and x2 other input along the y-axis, and the y is represented by certain colors or value that is equal to 0, 0 is representing to 0 output that is equal to black dot, and 1 output is represented by a red color. So now, what is my aim? My aim is to find a straight line or a hyperplane such that the output of a two-input logical OR gate can be separated. So now this output is depending upon the value of W1, W2, which is nothing but the weight, and the B that is nothing but the bias terms. If we consider this W1 is equal to 1.0 and W2 is equal to 1.0 and the bias term is equal to minus 0.5, so then I can say for 0, 0 input, the output is equal to negative minus 0.5. And for all other combination of the input, that is 0, 1, 1, 0 and 1, 1, I will get the output to be positive. So by using a simple threshold, I can able to separate the output of a two input logical OR gate. So this is the whole concept that how this perceptron is working. So in this case, this perceptron can able to work as the classes are linearly separated. The two output of a two input logical OR gate are linearly separated classes. So the same thing happens in case of a two input logical AND gate. So that means the output of a two input logical AND gate can be separated by the help of this perceptron. But what will happen in case of a two input logical exclusive OR gate? In case of a two input exclusive OR gate, we know that the output is equal to 0 if both the inputs are identical. That is for 0, 0, I am getting the output to be 0. For 1, 1, also I am getting the output to be 0. For rest of the combinations, that is 0, 1 and 1, 0, the output is equal to 1. If we represent the output of a two input logical exclusive OR gate in the form of a graphical representation, for 0, 0 it is giving 0 and 1, 1 also it is giving 0 and 0, 1 and 1, 0 it is giving 1. So I cannot able to separate the output of a two input exclusive OR gate by the help of a hyperplane, a single hyperplane. So for that reason, I have to require a two straight line. So how this problem that is faced by the perceptron can be overcome? This can be overcome by the help of different techniques. So these techniques are nothing but by using a multi-layer neural network, by using a Hopfield neural network, by using a radial basis function, by using this activation function. So the problem which we are facing in case of the perceptron, that can be overcome by the help of a multi-layer neural network or by the help of a Hopfield neural network or by the help of the activation functions. Now we'll try to understand how by the help of this multi-layer neural network, this problem can be overcome. So here I have taken one function that is called radial basis function. What basically this radial basis function is represent? This radial basis function makes a non-separable problems into a separable problem. Basically, how it will make the non-separable problem to a separable problem? This is performed by the increasing the dimensionality of the data. That means this will produce a non-linear transformations. In this case, radial basis function, there are some receptor is present that is represented by T. As we are moving away from the receptor, the value it basically increases or decreases. So this radial basis function basically maps the input vector that is equal to maps the input x into phi x. So here I have taken the radial basis function that is called the Gaussian function that will be represented by e to the power minus x minus t norm square. So now we'll see what exactly is happening in case of a two input exclusive OR gate by using this radial basis function. So this is a graphical representation of the input output for a two input exclusive OR gate, where the x1 and the x-axis and y-axis representing the input of the two input exclusive OR gate. So the colors are representing the output. Now here I have taken the four receptors that is equal to P1, P2, P3 as well as P4. If we consider any one of the receptor P1, then this P2 receptor and P3 receptor are equidistant from P1. Similarly, if I consider P2 receptor, then P4 and P1 are equidistant from P2. If I consider P4 receptor, P2 and P3 are equidistant from P4. Similarly, in case of P3. So that means what will be the spread or the variance that is called the standard deviation? For this, the standard deviation can be represented as that is equal to 1. So that will be represented by T is equal to 2. So as I have considered a Gaussian basis function, that means for phi 1, the P1 receptor and the sigma 1 is equal to 1. I can compute what will be your phi 1x. So that will be e to the power minus x minus t1 norm square. Similarly, phi 2x e to the power minus x minus t2 norm square, etc. So phi 1, phi 2, phi 3 as well as phi 4 are computed for the receptor that is equal to t1, t2, t3 and t4. So now for different input combinations, I should calculate what will be the value of a phi 1, phi 2, phi 3, phi 4. So I will get a 4 cross 4 matrix. So now for the different value of a phi 1, I will give a weight vector. That is for phi 1, I will give a weight vector that is minus 1.0, phi 2 1.0, phi 3 plus 1.0, and phi 4 minus 1.0. And I will calculate the summation of I is equal to 1 to 4 wi phi I. That will be equal to, for 0, 0, I am coming, it is giving to me minus 0.2, for 0, 1 plus 0.2, for 1, 0 plus 0.2, for 1, 1, that is minus 0.2. So from this, what we conclude? We conclude that for 0, 0 input, the output is negative. For 1, 1 input, also the output is negative. For other input combination, that is 0, 1 and 1, 0, the output is positive. So in this case, we seen that by the inputs are mapped into the two classes, that is equal to positive as well as negative. So by using the simple threshold or a binary threshold, I can able to separate the output of a two input exclusive order. So what radial basis function is doing? Basically, this radial basis function makes the 2D feature vector to a 4D feature vector. That means how this is performed? This is performed by the help of introducing a hidden layer, and this a hidden layer which basically is used to make a non-linearly separable classes to a linearly separable class. So what exactly this radial basis function is doing? As the radial basis function maps the 2D feature vector into a 4D feature vector, and this can be represented by introducing another layer into the network that is called the hidden layer. So the simplest neural network is now converted into a multi-layer neural network. That means some hidden layers are introduced. If there is more non-linearly separable classes, that means a more number of input layers, hidden layers are required for this case. So that means if there are multiple number of hidden layers are present, this will give rise to a multi-layer neural network. So this same kind of classification and the problem which it arises due to this non-linearly separable classes in case of perceptron can also be overcome by using the activation functions. People are using different kind of activation functions in the literature. Few of them have mentioned here: linear, bilinear threshold, sigma, tan hyperbolic, softmax, rectified linear unit, etc. So, but we will not talk about the other type of application, the activation function. We will talk only about the ReLU activation function, because this ReLU activation function is used in case of a deep neural network. So this ReLU stands for rectified linear unit, and it basically revolutionized the deep learning. So if we look into the ReLU activation function graphical representation, then we can see that the output is equal to the input if the overall input is greater than 0, and it has a constant gradient, or we can say that it has a constant gradient when the input is equal to or input is positive or input is equal to output, and it has a 0 gradient in these regions. So there are two versions of this ReLU is present. One is called the parametric ReLU, another is called the leaky ReLU. In case of this input-output relationship for the parametric ReLU can be represented as y is equal to maximum of 0, z plus beta minimum of 0, z. So beta can be represented as -1, that is equal to y is equal to z mod, absolute value of ReLU, and beta is equal to 0.01 for the leaky ReLU functions. Next is called the activation function, that is known as the softmax, and basically this softmax finds the probability of the ith class for a given input feature vector. So that means if we have some set of input vectors that is equal to x1 to xn, so in this case basically we are calculating what is the probability of yi is equal to 1 for a given input feature vector that is equal to x. So how it can be computed? It can be computed as exponential to the power wit, that is the transpose x plus bi, divided by summation j is equal to 1 to k exponential to the power wj transpose x plus bj, where this is small k represents the number of classes basically we are calculating from the input feature vectors. So this is the whole diagram. So in this case the x1 to xn are the inputs. So this b1 to bk are nothing but the bias terms. So similarly, W1 to Wk are nothing but the weight that is associated. So in this case, we are basically calculating what is the probability of y1 is equal to 1 for given input vector, y2 is equal to 1 for given input vector, like that. So this can help to finding or making the classifications. As already we have discussed, that the perceptron has a limitation is that it cannot able to separate a non-linearly separable classes. As it cannot able to separate non-linearly separable classes, we are introducing another layer into the network, which will make the number of layers more compared to the perceptron. So basically, if we increasing more and more number of hidden layers into the model, basically this will give rise to a concept that is called the deep learning or the deep neural network. Basically, this deep learning is a subfield of this machine learning concept. So if we look into this deep learning, this is a deep learning referred to as a deep structure learning, hierarchical learning, deep feature learning, and deep representational learning, etc. So these are most common and popular deep structures are nothing but multi-layer models. So if we compare this artificial intelligence, machine learning as well as deep learning, then we can see that this deep learning is a subset of machine learning, and the machine learning is a subset of this artificial intelligence. So this deep learning or the deep represents a successive layers of representation or multiple layers through which basically the data is transferred. So this is another representations where this machine learning, artificial intelligence, as well as the data science, all other things are present. So this is the neural network. This is the machine learning, and this is the reinforcement learning algorithm, short algorithms are present. So the data sciences consist of this machine learning as well as the statistics, linear regression, and artificial intelligence, a bigger set, I can say, which consists of machine learning, neural networks, knowledge modeling, symbolic reasoning, model logic, etc. So these are some of these diagrams of which we'll talk about these diagrams more in detail. I'm just skipping this thing. So if we look into this model that what we have discussed, that means we are seeing that as we are going increasing the number of layers into the neural network, it will give rise to a model that is called the deep model or the deep learning architecture or the deep neural network. There are various number of deep learning models that have been developed by the researchers. Few of them have been represented here. That is the LensNet, CNN, region-based CNN, faster RCN, neural networks, NACnet, DenseNet, RetinaNet, EfficientNet, etc. So there are still so many are present. You can have a look into the references. If we look into or the deep learning models, basically they are classified into a few categories. That is the convolutional neural network, recurrent neural network, stark autoencoder, deep Boltzmann machine, deep reinforcement learning. Any questions? Yeah, okay. So these are the main classification of this deep learning model. So if we look into the CNN, that is the convolutional neural network, basically the important component of this CNN is nothing but the convolutions. So we'll talk about what is this CNN. So in this case, the important part is the convolution. It has a multiple number of layers. If we look into the first layer can be able to find the edges or the raw pixels. The second layer can be able to find the simplest shapes. Subsequently, the higher layer can be able to extract some high features, that means coarse features, that is facial shapes and so forth. And the final layer can be able to help in the classification process. That is the high level features. So if we look into the deep learning models, this is a shallow ANN architecture, and this is a deep ANN architecture which is consist of multiple number of hidden layers. So this is a CNN architecture which is consist of a convolution, pooling, fully connected as well as output prediction. So if we look into the recurrent neural network, then or the LSTM, that is called long short-term memory network, then we can see that there is a feedback from the output to the hidden layers, or there is a self-feedback is present. So this recurrent neural network, can be considered to a deep generative architecture. In this case, the depth is large to that of the data input, basically in case of text data or the speech data, it is very large. So in this case, this recurrent neural network is popularly used because the length can be as large as possible, and it has one of the most important problems that it can have the vanishing gradient problem. As already I told you that during the time of learning, we are calculating the gradient. Basically, this gradient calculation helps to find the optimum value of weight. So the optimum value of weight will lead to the minimum MAC or mean square. So if the gradient is vanished or gradient doesn't exist, so what will happen? We cannot able to find the value of the weights. So this is one of the problems that we are facing in case of a recurrent neural network that is restricted due to the vanishing gradient problems. In this case, the optimization that is used, that is known as the stochastic gradient descent. We'll talk about this optimization techniques that are used in case of machine learning. Next is called the start autoencoder. Basically, this start autoencoder refers to an artificial neural network to learn coding by encoding a set of data. So it consists of an input layer, a smaller hidden layers, as well as the output layers. So this performs a data reduction task. Next is the deep Boltzmann machine. Basically, this deep Boltzmann machine consists of two layers. One layer is called the visible layer, and another layer is called the hidden layer. If we look into the architecture of this Boltzmann machine, then we can see that the nodes present in the same layer are interconnected with each other. So that means the nodes of visible layer are interconnected, as well as the nodes of the hidden layer also interconnected. And basically, this type of architecture is very ineffective in nature. So in order to overcome this type of difficulty, this connection between the neurons in the same layer is removed. So if we remove the connection between the nodes of the same layer, this is called the restricted Boltzmann machine architecture. So this restricted Boltzmann machine architecture has a visible layer as well as the hidden layer. Hidden layer, if we are connecting the output of this restricted Boltzmann machine to the input of another restricted Boltzmann machine, then this will give a stacked architecture. And basically, this stacked architecture is known as the deep belief network, or that is called the DBMs. So next is called the reinforcement learning. Basically, this reinforcement learning strengthens both the supervised as well as the unsupervised learning. Example is our Q learning concept. And so this is patented by Google, and the Q functions of the Q learning with a deep neural architecture is emerged, and the improved deep Q network that is called the double Q learning, prioritized experience replay, dealing network architecture. These are nothing but Q learning. So this is all about this deep learning. So if we look into this machine learning concept as well as this deep learning concept, then we can see that in case of machine learning, we are performing a feature extraction technique. That means the feature is get extracted. But in case of deep learning technique, we don't have to extract the features. So the features can be extracted automatically. That means already I told the layer which is very close to the input can able to extract some fine features, and the layer which is very far away from the input can able to extract some coarse features. So this is the difference between the deep learning versus the machine learning concepts. So if we look into the different components of the CNN, what are the components? That is the conventional neural network, which is the basic deep learning network. So it has an input layer. So basically, this input layer is represented by the four-dimensional tensor that is equal to n cross 3, which is the number of images. The convolution layer is a layer which will provide the feature map. So basically, this feature map depends upon the dimension of the kernel, size of the kernel, or the dimension of the size of the kernel. The next is the activation function that is called the ReLU is used. So basically, this ReLU represents rectified linear unit, which adds non-linearity into the network and provides non-saturating gradient. pooling layer, that basically downsample the 2D activation maps along the height as well as the width, and the fully connected layer in which each neuron is interconnected with all other neurons. So these are the different components that have been represented here: computational layer, value activation function, pooling layer, dense connection, and fully connected layer. If you look into the details of these components, the first layer is called the input layer. So these are nothing but the input images. So the input images are represented as a 4-dimensional tensor that is called image index as well as image dimension, and image dimension is represented by height, width as well as the channel. Next is the convolution layer. The convolution layer uses a coordinate that is known as a filter of size k is equal to m cross n, and based on the stride padding, it will generate the output that is known as the feature layer. So what is this stride? Stride basically represents the number of pixels to move in each special direction, and the padding basically appends 0 to the boundary of the image to control the size of the output conversion. So after this conversion, we are getting the output to be L minus K plus 2T divided by S plus 1, where K is nothing but the kernel size, L is nothing but the input image size, and P is padding, and S is called the stride. So this can be represented in the case of a 2D also. So what is the advantages of this convolution layer? So basically, if we are performing multiple number of convolution, that is known as the stacking convolution, and basically this stacking convolution is very effective in case of feature extraction by the help of the deep learning. So layers which are very close to the input can able to find the that is called line features, or can able to find some simplest features, and the layers which are very far away from the input can able to find some coarse features. So if we'll do a multiple number of convolutions, then it will give rise to an error. That means the precise position of the features in the input is recorded. So what exactly it represents? It represents if there is a small movement in the position of the feature in the input image, it will result a different feature map. And this occurs due to the recropping, rotation, shifting, that is due to the process of augmentation of the data, and other minor changes to the input image. And basically this limitation, which occurs due to the multiple number of convolutions, can be overcome by the help of this downsampling operations. So basically this also can be performed by changing the stride. Robust and common approach is nothing but the pooling approach. Basically this is a pooling operation, that means which will overcome the difficulty that arises due to the multiple number of convolutions. So this pooling operation is performed by the pooling layer, and basically it added after the non-linearity that is called the railing. So operates upon the each feature map separately to create a new setup for the same number of pooled feature maps. Summarizes the locality of an image being given by the kernel. So there are different types of pooling: max pooling, average pooling, as well as global pooling. In case of max pooling, maximum intensity value of the locality is considered. In case of average pooling, average value for each path on the feature map is considered. And in case of global pooling, downsamples the entire feature maps to a single value. So pool size is same as that of the feature map. So what this convolution is doing already, I have told that in case of convolution, we are using a kernel to make the convolution. So we'll directly go to an example of a 3D. So in case of a convolution, this is an RGB image, which is consists of RG as well as a B component, that is 3 input matrices, and there are 2 filters we have considered, that is equal to filter W0 and filter W1. The dimension of filter W0 is equal to 3 cross 3 cross 3, as well as the W1 is also 3 cross 3 cross 3. So after convolution, this will be summed up and it will give rise to the output. So this output is represented here. So this is the convolution output, and this is the pooling operation output, how the pooling operation is performed. So as we have discussed, there are 3 types of pooling: max pooling, average pooling, as well as global pooling. So this pooling operation provides translation invariance, distortion invariance, as well as a transformation invariance. So this is called the back propagation. Basically, during the time of back propagation, we are calculating the gradient, and this gradient will help to find the value of this weight matrix. So next is called the dropout layers. If there is a too much cooperation between the neurons, it makes the neurons to dependent on each other and they fail to learn the distinct features. This leads to overfitting conditions. So in order to overcome this problem, some of the neurons have been dropped and basically this will avoid the problem of the overfitting. Next, we will call to the calculation of parameters. I hope there is a break for 15 minutes.
Yes, sir.
So shall I stop here? Can I join after at 11:15?
Yes, sir. We are announcing the break from 11 to 11:15, sir.
Okay.
Can I announce, sir? Can I announce the break for participants?
Yes, madam. Sure, madam.
Okay.
Yeah.
So now it is the time for the tea break. Now I request all of you to kindly assemble here at 11:15 a.m.
Good afternoon or good morning.
Good morning,
should we
sir.
start?
Good morning,
Yes,
sir.
sir. Good morning, sir. Good
Welcome
afternoon.
back, sir.
Yeah. Should we start or will we wait for some more time?
Yes, sir. Yes, sir. We will start the session.
Okay, thank you. Again, I have to share. It is already shared. Can you able to see my screen? Hello.
Sir, please, sir.
Can you able to see my screen?
Yes, sir. You can start, sir.
No. The screen is visible to you.
No, sir. Please share your screen, sir.
1 minute. Now, is it visible, sir?
Yes, sir.
Yeah, fine. A few minutes back, we have discussed about the different components of the CNN. So now we'll talk about what are the parameters of the CNN. That means, as we told, the neural network is converted into a multi-layer neural network. That is basically deep neural network. So when we are talking about deep neural network, and each layer, maybe some of the layers is associated with convolution. Few of them are dropout layer. Some of them are the pooling layer, radio activation functions, max pooling layer. So that means the different parameters are associated with the calculation of the CNN. So what basically these parameters, and these parameters helps to tell about how complex the network is, or how much time is required to train the network. Basically, under this category, we are calculating the size of the layer after each completion. So it is known as the activation size, and basically this activation size is represented as the product of width, height, as well as the number of channels in the current layer. Sorry. So the activation size is equal to width, height, as well as the channels in the current layer. So these are the activation size that has been computed for this AICTE-ISTE. So next we'll come to about the parameters. How the parameters are computed. The number of parameters in a given layer depends upon the learnable layers. What do we mean by learnable layers? Basically, the layers which are take part in calculation of the weights, or which basically helps in calculating the weight in the back propagation algorithm. So these learnable layers learns the value of the filters. The value of the filter is the value of the weight by the back propagation algorithm. So that is the launch the weight of the matrix parameters. So those layers which are basically giving the value of the weights are nothing but the learnable layers. So from these learnable layers, we can calculate the number of the parameters. So input layer doesn't take part in the calculation of the parameters or during the learning process. As it doesn't take part in the learning process, the number of parameters in case of input layer is equal to 0. Compilation layer basically depends upon the width of the filter, height of the filter, the number of layers in the, or the number of filters in the previous layer, the filters used in the current layer, as well as the bias term. So the number of parameters that is computed from the convolution layer is depending upon the width of the filter, height of the filter, number of filters present in the previous layer, in +1 into k. K is nothing but the filters in the current layer. So this convolution layer gives rise to the calculation of the parameter. Pooling layer doesn't take part in the process of computation, or doesn't take part in the learning process. So the number of parameters in case of pooling layer is equal to 0. The fully connected layer, it contains the highest number of parameters because each neuron is connected to the every other neurons. So this can be computed as the number of parameters of the fully connected layer can be computed as the number of neurons in the current layer into the number of neurons in the previous layer +1 into the number of neurons in the current layer. So here I have taken one example of a CNN network in which one input layer is present, two convolution layer is present, two pooling layer is present, and two fully connected layers. So if we look into the number of parameters, in case of convolution 1, the number of parameters computed to be 608, and whereas convolution 2, it is 3216. So basically, this depends upon the depth of the layer as well as the number of filters present in the current layer. So if we look into the FC3, that is the fully connected layer 3, so the number of parameters which computed to be 38,120, which is found to be the highest among the number of parameters presented or computed in the other layers. So from this we understood that the fully connected layer provides the highest number of parameters compared to the other layers present in the CNN network. So this number of parameters basically gives rise to the complexity of the network. If there are more number of parameters, that is the more computational time is required for the training process as well as the training process. If we look into the standard deep neural network architecture, a large number of deep neural network architecture have been suggested by the different researchers for different kind of applications. Few of them have been noted down here. And mainly, if we look into the different deep neural network architecture, mainly they are performing the task of classification. And few of them, like UNet, PSPNet, SegNet, these are used for the performing the task of the segmentations. So these different pre-trained networks, the information like the depth of layer, connections, parameters, input layer, data set, and for which purpose it was developed have been summarized in this slide. I'm not going through the details of this. You can have a look into that. When it was developed, what are the number of parameters for which purpose it was used have been summarized here. So have a look into this. So while we are using this deep neural network architectures, basically we are performing the work of classification, another is the work of the segmentation. When we are performing the work of a classification or task of a classification, basically the classification is proper or not. For that reason, we are using one error calculation that is known as the top 5 error. So what is basically this top 5 error rate? This top 5 error rate is the fraction of the test image for which the correct label is among the top 5. So here one example is given. This is the, if you look into the left side figure, left corner of the figure, then it is nothing but a mite. What is the probability that it is a mite? What is the probability that it is a black widow? Probability that it is a cockroach? Probability that it is a tick? Probability that it is a starfish? That means top 5 error rate is the fraction of the test image for which the correct label is among the top 5. Similarly, the top 1 error rate is the fraction of the test image for which the correct label is the one just most likely to be by the model. That will be computed by the error rate. Similarly, there are the RSNet is used. In case of RSNet, there is a feedback from the previous layer to the current layer. So that means this layer is known as the feedback layer. So if we'll say this is equal to f of x, this x is directly coming. So this will give rise to fx plus x. And this basically perceived better than the human error. So in this case, the accuracy is found to be high compared to the other networks. Unit architecture, this is a special kind of architecture which is used for the segmentation purpose. So this type of architecture or this type of network has a look like, or this type of network is looking like a U-shape. It was one contracting path that is known as the encoder and an expanding path that is known as the decoder. So basically, this expanding path localizes the high resolution features, and this contracting path that is known as the encoder basically reduces the size of the image, and expanding path increases the size of the image. So basically, this is used for semantic segmentation. So similarly, SegNet, it is also used for segmentation purposes. Next is PSPNet, also it is used for the semantic segmentations. So these are the few of the networks which are used for the segmentation, and most of the networks are used for the classification purposes. So what is semantic segmentation? If we look into basically in case of a segmentation, we are finding the region of interest. But in case of semantic segmentation, each pixel is labeled with an object class. Basically, this facilitates the description, categorization, and visualization of regions of interest in an image. So that means, in other words, I can say that the semantic segmentation can able to find what is present and where is present. So both this information can be computed by the help of semantic segmentation. So what is present? So what are the different information is present, and location where is present. So these two information we can get from the semantic segmentation. Here, one semantic segmentation is used in case of automatic driving car. So how the semantic segmentation is performed for segmenting the different regions. So this is semantic segmentation uses one technique that is known as the transposed convolution, which is nothing but a factorially stride convolution or the deconvolution for performing this operation. So what we have discussed, we have started that with a fuzzy logic. In fuzzy logic, we have seen that fuzzy logic can be efficiently used in terms of this artificial intelligence of the deep neural network for handling a huge amount of data or the big data problem. So this, whenever we are talking about a big data, basically we are talking about this neural network or the deep neural network, and the deep neural network, the main component is nothing but the neural network. Basically, in case of a simplest neural network like perceptron, we are facing a problem that it cannot able to separate the non-linearly separable classes. So for that reason, researchers have introduced more and more hidden layers into the neural network. So when they are introducing more and more hidden layers, basically the dimensionality of the data increases. As the dimensionality of the data increases, basically the 2D feature vector basically mapped into a 4D or a multi-dimensional feature vector, which helps in converting a non-linearly separable classes to a linearly separable classes. And this gives rise to introduction of a deep neural network. And this deep neural network mainly becomes more popular due to the ReLU activation function as well as softmax layers. So this the ReLU activation function introduces non-linearity into the network, and this deep neural network depends upon the number of parameters. The complexity of this deep neural network depends upon the number of parameters. So if we look into the limitation of this deep neural network, basically this deep neural network looks like a black box and it is very, very data hungry. So that means a huge amount of data is required, or the training data is required to make the network to be overfitting or to avoid overfitting conditions. And this deep neural network is computationally intensive. And that means to train a longer or it requires a huge training time as well as a dedicated GPU is required for this. This type of network is easily fooled by the adversarial examples. It is subjected to algorithmic bias. It is poor at representing uncertainties, uninterpretable black boxes, and difficult to trust, and requires expert knowledge to design, fine-tune, etc. So these are nothing but some of the limitations of this deep neural network architectures. So this is the thing that we have discussed. Now we'll talk about the optimizations. Basically, as I already told, whenever we are talking about this deep neural network, basically we are calculating the value of weight. The value of weight is computed based on the calculation of the gradient. So the gradient should not vanish. So as if the gradient will vanish, then we cannot able to find the value of weights. So in order to overcome that type of difficulty, people are using this ReLU activation functions. People are using the dropout layer. People are using the different optimization techniques. What are the different optimization techniques people have used to calculate the value of weights? This optimization technique helps in finding the weight values. So here we will talk about what are the optimization techniques basically researchers have used for finding the value of weight or the optimization method. Under this category, we will talk about optimization problem, optimization method, application and development of optimization method in some case of a popular MLC, and what are the challenges basically we are facing in case of optimization. If we look into the optimizations, basically this optimization is the core component of the machine learning, because the machine learning popularity depends upon the optimization itself, because during this optimization process we can able to find the value of the weight. So once we can able to find the value of the weight, the error will get minimized. So the efficiency and effectiveness of the optimization algorithm is influenced by the popularity of this machine learning algorithm. So if we look into the types of optimization, there are mainly three types of optimization techniques that people have used. One is called the first order optimization, under which the stochastic gradient is coming into picture. One is called the high order optimization, in which the Newton's method is used. Another is called the heuristic derivative free optimization, where people are using the coordinate descent method. So what is first order optimization? Basically, one of the popular examples of this first order optimization is called the stochastic gradient, and it's a variance or it's a types. This is less attention by the researcher because using the optimization as a black box that limits the functionality, and it has a lower convergence. Lower convergence means in order to make it to, or in order to get the optimized value, it requires a lot of time. So for that reason, people are started using the high order optimization. Under this category, the most popular technique that people are using, that is called Newton's methods. It has a faster convergence compared to the stochastic gradient. That means we can able to reach at the optimization point with a faster rate or with less time. In this case, the curvature information makes the short direction is very effective as well as efficient. Attract widespread attention, but face more challenges for storing the inverse matrix. So it has a challenge of storing the inverse matrix problem occurs. The next is called heuristic derivative free optimization. This is a coordinate descent method used in case where the derivative of the object function do not exist or the difficult to calculate. So sometimes I told you that we are calculating the gradient with respect to W such that we are getting the optimized value of or we are getting the value of W. So sometimes this derivative doesn't vanish or derivative doesn't exist or it will vanish. So for that case, the heuristic derivative free optimization techniques are used. So the idea behind this method is that heuristic based on some empirical rule and fitting the objective function with respect to some samples. So if we look into the ML problems that are formulated and solved by the optimization method, so optimization in DL encounters various problems and challenges. DL, so as already I have discussed, the DNN are mainly classified into 5 groups, but the most popular types are nothing but the CNN, convolutional neural network, as well as the recurrent neural network. In case of convolutional neural network, that is a feed-forward network. There is no backward propagation. That means there is no feedback is present. But in case of recurrent neural network, there is a sequential model and popular in case of natural language processing, text processing, or speech processing. Basically, why this is popular in these cases? Because there is a feedback and it can take as much length to that of the data sequence. So these are the two main techniques that we are discussing, that is CNN as well as the recurrent neural network. So the stochastic gradient is mainly used in case of DNN, but leads to a various type of problems. What are the problems that we are facing in case of stochastic gradient? Basically, this stochastic gradient is depending upon one parameter, that is nothing of the learning rate. If the learning rate is very, very small, then it will take a lot of time to come into the convergence. If the learning rate slightly increased or improved, sometimes what will happen, we may reach the convergent point with a faster rate, but sometimes we may not converge. If the learning rate will be too high, then what will happen? It will diverge out. It will not converge at all. That means it will give rise to one problem that is called the oscillating problem. It is oscillating during the latter training stage of the sum of the adaptive methods and may not converge. Optimization is based on the variance is proper to improve the convergence. Stochastic gradient and its variance may improve the optimization. Stochastic gradient descent can improve the accuracy and convergence state. Next is called the meta-learning, which is popular in this machine learning due to the adaptation of new environment with a few samples. So under this category, supervised learning, that is types metric-based method, model-based method, optimization-based methods have been used. So what are the challenges that we are facing in case of this machine learning? So how to improve the optimization performance with insufficient data? Already we have discussed that this deep learning techniques requires a very huge amount of training data. So that means it is very, very data hungry. But if we look into the practical applications, we may not able to get sufficient amount of data. Take the example of medical data or the cancer data. Take the example of a COVID data. So the data, that means we are not getting enough data or insufficient amount of data is present. So how the optimization algorithm can perform better, or how the improvement can be possible for the optimization algorithms for the insufficient amount of data. So less data in the training causes the problems of very high variance and overfitting. So non-convex optimization makes the optimization locally and optimal, but not globally optimal. So how to analyze the deviation of the stochastic optimization in case of sequential models? Because the sequential model samples are truncated and fed in batches. Take one example of the speech data. In case of a speech data or in case of a text data, it is very long. So when we are feeding this data into some optimization model, basically we are truncated into some few samples, or we are truncated by the help of a window. So how we can truncate it? How to analyze the deviation of the stochastic optimization in case of sequential models? So how to truncate? So or how to fade in terms of batches? So stochastic variation inference is graceful and practical, and it is probably a good choice to develop methods of applying high order gradient information to stochastic variational interferences. So powerful optimization can be achieved by introducing a stochastic technique to the conjugate gradient method. Improvements in stochastic conjugate gradient is a challenging problem. So what are the points that we are going to discuss here? That is the ML problem from perspective of optimization, classification of optimization and their latest developments in case of machine learning, development and applications of the optimization in some specific machine learning applications, challenges and problems. If we look into the objectives of our machine learning, basically this is builds a model and constructing one objective function. And for determined objective function, appropriate numerical and analytical optimization methods are used to solve these optimization problems. So the classification of machine learning according to the modeling already we have discussed, they are classified into supervised, semi-supervised, unsupervised, as well as reinforced. Again, supervised perform two tasks. We have already discussed, that is classification and regression. Semi-supervised, self-supervised also we have discussed. In case of unsupervised, we are performing the tasks like clustering, dimensional reduction. Reinforcement doesn't require any fixed kind of databases. So now, what is our aim in optimization? Our aim or the goal in case of optimization is that find an optimal mapping function to minimize the loss function of the training samples. What is this mapping function? This mapping function, can I take it as fx? So now we have to make this mapping function to minimize the loss. We have to how to minimize the loss. That can be represented as minimum of theta 1 upon n, where n is representing the number of samples. I is equal to 1 to n. L, that is the loss function yi f of xi theta. What is this n? This capital N represents the number of training samples, and theta is the parameter of the that is the mapping function, and xi is the feature vector for the ith sample, and yi is the corresponding label, and n is the loss function. So what is our n in case of optimization? In case of optimization, we have to find a mapping function such that the loss has to be minimum, or we have to minimize the loss for the whole number of samples, or for the total number of training samples. And in this case, I have considered that theta is the parameter of this mapping functions. So now, based on these types of loss functions in supervised learning, they can be such as square or equivalent distance, cross entropy, contrast loss, hinge loss, information gain, etc. If we look into the regression problem, that is equal to square or equivalent distance is used as a loss function that minimize the square error, as already have discussed in case of regression analysis. Generalization error, what will happen to this regression problem? Sometimes this generalization error may not be sufficiently low, it will be too high. So these are the things that we are getting. So another form of structural risk minimization, which representation can be method in case of a support vector machine. So in case of support vector machine, an objective function regularization items are usually added to alleviate the overfitting condition. That is in terms of L2 law. So minimum of theta can be represented as 1 by n, I is equal to 1 to n, L of yi, f of xi theta, where f is nothing but the mapping function, yi is called the level, L is the loss function, and n is the total number of samples. And in this case, one extra parameter is used that is equal to lambda, and this lambda is nothing but compromise parameter to determine through cross validations. And theta is the parameter lambda of theta norm square. That is nothing but the L2 norm. Sorry. So now, in case of optimization, in case of semi-supervised learning, how does semi-supervised learning is perform the optimization? Between supervised and unsupervised, this semi-supervised is coming into picture. It uses both labeled as well as unlabeled data during the time of training. So the task which is performed by this semi-supervised learning are classification, regression, clustering, dimensionality, induction, etc. If we look into the different types of semi-supervised learning, there are self-training methods, generative models, semi-supervised support vector machine, graph-based methods, multi-learning methods, etc. So how the optimization is performed? The optimization in semi-supervised SPM deal with a binary classification and part of training set is labeled. How it can be? So DL, this is stands for the labeled data that can be represented as x1, y1, x2, y or x square y, x2, y2, or xl, yn. So in case of unlabeled data, this will be x of n plus 1, x of n plus 2, up to x of n. So here this n is represented to L plus a. So there is some typographical error, it is overlapped. So n is equal to L plus a, and to use the information to unlabeled data, additional constraint on the unlabeled data is added with addition to the original objective of the SPM with a slack variable. And what is that slack variable? This slack variable can be represented by this zeta I, and this sigma j is represent the misclassification error for the unlabeled instances if the true label is positive, where g to the power j is represent the misclassification error of the unlabeled instances if the true label is negative. So what is our aim? Our aim is to minimize this sigma, or that is equal to epsilon to the power I, zeta to the power I. That is equal to the minimum. That is equal to j is equal to L plus 1 to n summation minimum of this summation, that is epsilon I and zeta j should be very, very small. So this is the constant, or this is the thing that we have to optimize, or we have to make it to be very, very small. So a semi-supervised problem can be described as the minimum of omega plus c, I is equal to 1 to L, zeta to the power I plus I is equal to 1 to L, minimum of epsilon to the power I, zeta to or g to the power j. So where c is representing a penalty coefficient, so this can be represented as y to the power I, w xi b plus zeta to the power I greater than or equal to 1 if this is the condition to be satisfied. If w into x to the power j plus b plus epsilon to the power j should be greater than 1 if epsilon is greater than 0, and minus w dot x to the power j plus b plus g to the power j greater than or equal to 1, where z to the power j should be greater than 0. So in this case, in case of semi-supervised optimization, the learning is a mixed integer problem. So process is to deal with the problem that is called branch and bound technique, and context relaxation methods are used in this case. In case of unsupervised learning, basically how this optimization is performed in case of unsupervised learning. So as already we know that this unsupervised learning is used mainly for clustering. Clustering means we are grouping the total database into different clusters. So this aim of this clustering is to divide the group of samples into a multiple cluster such that the differences between the samples of the same cluster are small and the different clusters are large. So the optimization problem to minimize the following loss can be represented as minimum of S k is equal to 1 to capital K, x belongs to Sk, where this is capital Sk represents the sample set of the cluster, norm x minus mu k L2 norm. So where K, capital K represents the number of clusters, small x that represents the feature vector of the samples, and mu k is representing the center clusters. And the capital Sk sample set of clusters, okay. So the sum of the variances of the clusters are small. That means it should be very, very small or as small as possible. So basically, this is used for the dimensionality reductions. So what basically this dimensionality reduction problem tells? This dimensionality reduction problem tells that original information of the data is retained as much as possible after projecting them to a low dimensional space. So that means when the high dimensional data is projected into a low dimensional space, the original information should be retained. So this is one of the best examples. It's called the principal component analysis. In case of principal component analysis, the aim is to minimize the reconstruction error. How to minimize this reconstruction? What is the optimization criteria? So in this case, if we consider this capital M is equal to number of samples and x to the power I is equal to the d-dimensional vector and x to the power I bar is called the reconstruction of x to the power I and g to the power I is represent z1i, z2i up to zdi is the projection of xi into a d-dimensional coordinate. Then E of j is called the standard orthogonal basis under the d-dimensional coordinate. So basically, we are calculating the minimum of I is equal to 1 to n xj bar minus xi norm square, where xi bar is equal to j is equal to 1 to d zj to the power I ej and d is greater than d. So another optimization also used for this principal component analysis, and the goal is to the probabilistic model to find the optimal probability density function that is equal to px, which maximizes the logarithmic likelihood function. So the logarithmic likelihood function has to be maximized for calculating the principal component analysis that can be represented as maximum of I is equal to 1 to n logarithmic of p of xi theta. So this is the way how we are performing the optimization in case of unsupervised learning. So how the optimization is performed in case of reinforcement learning. Already I told, in case of reinforcement learning, there is one agent is used and one environment is used. So there is a feedback from the environment to the agent. So based on the feedback, the agent has to perform a task such a manner that the reward is best maximized. So this is the strategy. This is the principle that is used in case of reinforcement learning. So how the optimization is done by the, or what is the optimization function? So basically, it uses an optimal strategy function which output varies in the environment. So there are two types of strategies people are using. One is called deterministic strategy, another is called uncertain strategy. So in case of deterministic strategy, the mapping function for state S to action A is the learning target. So that means if the state S is known to us, the action for the particular state S is also known to us. So the mapping function from state S to A is called the learning target. In case of uncertainty strategy, the probability of executing each action is called a learning target. So how the action is performed? So action is equal to A is equal to pi of S, where pi of S is known as the policy function. So optimization problem in reinforcement learning can be formulated as maximizing the cumulative return after executing a series of actions which are determined by the policy function. And how this policy function can be represented? So maximum pi v by s. So now this v by s can be represented as the expectation of k is equal to 0 to infinite gamma to the power k r to r of t plus k such that st must be equal to s. Where this value function of the state s under the policy pi can be represented as v by s, and where r is nothing but the reward and gamma is nothing but the discount factor that is nearly equal to 0.1. So the main steps in ML is to build a model hypothesis or define an objective function. That is the aim of the modeling problem in case of a machine learning. So in case of optimization, basically what we are doing, we are solving a function or a mapping function or finding the maximum or minimum of the objective function to determine the parameters of the model. So what are the parameters of the model? Parameters of the model is nothing but your weight vector. So aim is to solve a desired model optimization methods. So how to solve it? So already I have told the solving can be done by the first order optimization, higher order optimization, as well as derivative-free optimization methods. So what is this first order optimization method? As already we have discussed, the first order optimization methods are mainly based on the gradient-based approaches. The first order optimization method, gradient-based method approach is not very new. It is the earliest and most commonly used method in case of optimization. So these variables update iteratively in the opposite direction of the gradient of the objective function. So in this case, what exactly is happening? It will update the value or update the variable or update certain parameter iteratively in a direction opposite to the gradient of the objective function. So the update is performed gradually to convert the optimal value of the objective function. So the learning rate is that is known as the beta or eta. We can say that this is eta, which determines the step size in each iteration and thus influences the number of iterations to reach the optimum value. Next is called the steepest descent algorithm, which is also very popular. The idea of this steepest descent algorithm is to select an appropriate source direction in each iteration so that the value of the objective function minimizes the in a faster way. So if we look into the gradient descent and steepest descent, then these both are not the same, because the direction of the negative gradient doesn't always make a descent to be fastest. So gradient descent is an example using of inclined norm in the steepest descent. So the formal expression for the gradient descent can be represented for a linear regression that is equal to f theta x, where the function is to be lost and the n theta is nothing but a log that is called the loss function, and theta is called the parameter which is to be optimized. So the main aim or the objective is to minimize the loss function that can be minimized by this formula that is equal to L theta is equal to 1 by 2n, I is equal to 1 to n, y to the power I minus f theta xi whole total square. What is this f theta? This f theta can be represented as j is equal to 1 to d theta j xj. And what is this capital D? This capital D represents the number of input feature vectors, and the capital N is representing the number of training samples. And x to the power I, this is nothing but the independent variables that is taken as xi of can be represented as x1 I, x2 I of the STI, and where I is equal to 1 to n, and yi is nothing but the target output. So gradient descent alternates the following two steps until convergence. What is the two steps? It is alternate between the till it is achieving the convergence. One is called the derive the gradient and update the parameters. So that means the gradient is calculated for each iteration as well as the parameter is updated for each iteration. So these the two processes each followed, or the two processes each continue till the convergence is reached. So what is the calculation of gradient? The calculation or the derivation of the gradient is represented by del of L theta divided by del theta j, that is equal to minus 1 upon n, I is equal to 1 to n, yi minus f theta xi into x to the x of j. So the update parameter can be represented as theta j dash, that is equal to theta j plus eta, where this eta is representing the step size, or that is called the learning factor, into 1 by n, I is equal to 1 to n, yi minus f theta xi xj. So now what is the beauty of this equation? So the beauty of this equation is that this total updating depends upon this eta. So if the eta is very, very slow or very small, so that means the optimization process is very slow, sluggish, and it will take a lot of time. If eta is large, then we may reach at the optimization. Sometimes we may not reach at the optimization point. If eta is too large, then it will converge, it will not converge, it will diverge out, and some value of theta, it will oscillate, start oscillating. It will never come to the optimization point or the optimization point. So what we understood from this gradient descent method, the gradient descent method is very simple to implement. Solution is global optimal when the objective function is convex, often converges at a slower speed if the variable is closer to the optimal solution, and more careful iteration need to be performed in this case. There are some few points about this. All the training data are used in each iteration step, so the gradient descent method is also called the breadth gradient descent because all the data points are being used. If the number of samples is n and the dimension of x is d, the computational complexity for each iteration can be represented as the order of n into d. In order to mitigate the cost of computation, some parallelization methods have been also proposed. However, the cost is still hard to accept when they are dealing with a large scale of data. The stochastic gradient descent method emerges due to the above difficulties or to overcome the difficulties. So what is this stochastic gradient? Basically, in case of stochastic gradient, a back gradient descent has high computational complexity in each iteration for large scale data and doesn't allow online update. So stochastic gradient descent idea is to use one sample randomly update with the gradient for iteration instead of directly calculating the exact value of the gradient. So the stochastic gradient is an unbiased estimate of the real gradient, and the cost of the stochastic gradient descent algorithm is independent of sample number and can achieve some linear convergence speed. Stochastic gradient reduces the update time for dealing with a large number of samples and removes a certain amount of computational redundancy, which significantly accelerates the calculation. In strong convex problem, the stochastic gradient can achieve the optimal convergence speed. The loss function that is used in this case that can be represented as L of theta that is equal to 1 by n, I is equal to 1 to n, 1 by 2, yi minus f theta xi whole square that is can be represented as 1 by n, I is equal to 1 to n cos theta xi yi. Next is the Lestrop accelerated gradient descent. Idea of applying the stochastic gradient to preserve the influence of the previous updated direction on the next iteration to a certain degree. So how we can able to store the previous direction? So that is the whole idea of this Lestrop accelerated gradient descent. So the momentum method can speed up the convergence when the dealing with a high curvature or small but consistent gradient or the noisy gradient. So the momentum algorithm introduces the variable v as the speed which represents the direction and the rate of the parameters movement in the parameter space. The speed is set as the average exponential decay of the negative gradient. Next is the adaptive learning rate method. The manually regulated learning rate greatly influence or the effect of the stochastic gradient method. So it is a tricky problem for setting an appropriate value of the learning rate. Some adaptive methods were proposed to adjust the learning rate automatically. So these methods are free of parameter adjustment, fast to convergence, and often achieve not bad results, while used in case of deep neural network to deal with the optimization problems. So what are these adaptive methods? These adaptive methods are ARA-GRAD, ARA-delta, ARA-MESTROC, ADAM, that is known as the adaptive movement estimations. So what is the ARA-GRAD? Basically, this is a straightforward improvement of the stochastic gradient, and ARA-GRAD adjusts the learning rate dynamically based on the historical gradient in some previous iteration. The update formula for this ARA-GRAD can be represented as G T del of L theta d theta, where this represents the gradient of parameter theta at the iteration t, and Vt is represented as I is equal to 1 to 2 Gi whole square plus epsilon. Basically, this accumulates the historical gradient of parameter theta at the iteration t, and where the updating rule can be represented as theta t plus 1 that is equal to theta t minus eta gt by Vt, where theta t is the value of the parameter theta at iteration t. So the difference between the ARA and the gradient descent is that during the parameter update process, the learning rate is no longer fixed, but it is computed using the historical gradients accumulated up to these iterations. So this ARA uses a historical gradient accumulated till the iteration point is used. One of the main benefits of this ARA is that it eliminates the need of to tune the learning rate manually, as in case of stochastic gradient, we are tuning the learning rate. In this case, the tuning is not required. So most of these researchers have used this learning rate in case of ARA to be 0.01. What are the issues with this ARA? The algorithm still needs to set the global learning rate, that is equal to eta manually. As the training time increases, the accumulated gradient will become larger and larger, making the learning rate tend to 0 and resulting in effective parameter to update. So this is one of the serious issues with the ARA graph. In order to overcome this type of difficulty, researchers come up with a technique that is called ARA delta. So this ARA graph was improved to ARA delta or RMS prop. The idea is to consider not accumulating all the historical gradients, but focusing only on the gradients in a window. That means a few of the historical gradients have been accumulated. That means depending upon the window size, the gradients are accumulated over a period. And using the exponential moving average to calculate the second order cumulative movement, that can be computed as Vt is equal to beta Vt minus 1 minus beta Vt whole square. Where this beta is nothing but exponential decay parameter. Next is called the ADAM, that is known as the adaptive movement estimation. So advancement in GCD, that is a stochastic gradient method, which introduces an adaptive learning rate for each parameter. It combines adaptive learning rate and momentum method. In addition to storing an exponential decaying average of a past square gradient Vt like ARA delta, RMS prop, ADAM also keeps an exponential decaying average of the past gradient MT, which is similar to the momentum method. Next is the variance reduction method. The variance reduction method due to a large amount of redundant information in the training samples. These stochastic gradient methods are very popular. Stochastic gradient method can only converge at a sublinear rate, and the variance of the gradient is often very large. How to reduce the variance and improve the stochastic gradient to a linear convergence has always been an important problem. And there are two types are being used for this. One is called stochastic average gradient. Another is called the stochastic variance reduction gradient. What is stochastic average gradient? In case, basically, in case of stochastic average gradient, the variance reduction method proposed to improve the convergence speed, and stochastic average gradient method maintains the parameter of recording sum of the n largest gradients in memory, where Gi is calculated using one sample, that is equal to I, where I belongs to 1 to n. Only applicable to smooth and convex functions and needs to store the gradient of each sample. It is convenient to be applied in case of non-convex neural network. Stochastic variance reduction gradient method was proposed to improve the performance of the optimization in some complex models. SPRG maintains the interval average gradient, that is equal to mu bar, by calculating the gradient of all the samples in every window iteration instead of each iteration. So next is called the high order methods. What are the high order methods? The high order methods are nothing but the second order methods can be used for addressing the problems where the objective function is highly nonlinear or that is ill-conditioned. They work effectively by introducing a curvature information. So high order optimization methods are applied to handle large scale data. So some of the few of the examples are conjugate gradient method, quasi-Newton method. So this is a high order method under this category: quasi-Newton method, quasi-Newton conditions, DSP, DSGS, LBSGS are used. Next is called a high order method, that is stochastic quasi-Newton methods, Hessian-free methods have been used. So few of them have been noted down here with their advantages and disadvantages. So if we look to the gradient descent, basically the aim of this gradient descent is to solve the optimal value along the direction of the gradient descent. And this method converges at a linear rate. If we look into the advantages of gradient descent, the solution is global optimal when the object function is convex. If we look into the disadvantages of this gradient descent, then each parameter updates the gradients of the total samples need to be calculated. So the calculation cost is too high in this case. So if we look into the stochastic gradient and compare with the gradient descent, then the stochastic gradient descent, the update parameters are calculated using randomly sampled mini-gaps, and the method converges at a sublinear rate. And the advantages of the stochastic gradient is that the calculation time for each update doesn't depend upon the total number of training samples, which was previously a disadvantage for this gradient descent. And if we look into the disadvantages of the stochastic gradient, it is difficult to choose an appropriate learning rate, which is one of the major disadvantages. Sometimes it will diverge out, sometimes it will take a lot of time. So that means choosing of this learning rate is one of the most important tasks in case of stochastic gradient descent. So the solution may be trapped at some saddle point in some cases. There is an accelerated current gradient descent by accumulating the previous gradient. So the advantages of this, when the gradient direction changes, the momentum can also slow the update and update speed and reduce the oscillations. When the gradient direction remains, the momentum can accelerate on the parameter update. So the momentum helps to jump out some locally optimal solutions. It is difficult to choose a suitable learning rate in case of this process also. So next is coming the AICTE-ISTE, that is nothing but the adaptive method. The adaptive method, the learning rate is adaptively adjusted. You don't have to, or a person don't have to adjust the learning rate. The advantages is that in the early stage, the training of cumulative gradient is smaller and the learning rate is larger, and the learning speed is faster. The method is suitable for dealing with sparse gradient problems. The learning rate of each parameter adjusts adaptively. As the training time increases, the accumulated gradient will become larger and larger, and making the learning rate tend to 0, resulting in parameter update. A manual learning rate is still needed. It is not suitable for dealing with non-convex problems. If we look into the ARA delta and ARA stroke and compare with ARA graph, the change the way of the total gradient accumulation to exponential moving approach, improve the ineffective of learning problem in the late stage of ARA graph, and it is suitable for optimizing non-stationary, non-convex problems. In the late training stages, the update process may repeated around the local minimum. This is the disadvantage of this ARA delta and ARA stroke. If we look into the ARA, it combines the adaptive methods and momentum methods used in the first order moment estimation and the second order moment estimation of the gradient dynamically, and adjust the learning rate of each parameter, and add the bias correction terms in case of ARA. So this has the advantages that the gradient descent process is relatively stable. It is suitable for most non-convex optimization problems with large data sets and high dimensional space. The method may not converge in some applications. Next is this is SAG and SVRG. Just have a look into these higher order methods. So these are some of the higher order methods of this optimization. So what are the challenges we are facing during the time of optimization? So the challenges that we are facing during the optimization of these techniques in case of machine learning approaches, that is the complexity of this machine learning model. The challenges in DNN that it has a very less amount of data, insufficient of data in training the DNN. Non-convex optimization in DNN. Difficulties occurs in case of sequential models with large scale data. High order methods for stochastic variational inference. Stochastic optimization in case of conjugate gradient. So these are the few of the challenges that we are facing in case of the optimization techniques. So anybody want to ask any questions? So these are the things that how the optimization is performed in case of a machine learning that we have discussed here, particularly in case of deep neural networks. Next we will talk about this neuromorphic computing in AI-enabled hardware based Hopfield neural network. So we are doing with this neural network. So the neural network is converted into the deep neural network because the introduction of the large number of hidden layers into the network. So it will give rise to a deep neural network. So now we'll talk about this another concept that is called neuromorphic computing. This neuromorphic computing is nothing but the similar kind to that of the artificial intelligence, which is mimicking our human brain. So how the human brain is basically working the same principle. This neuromorphic computing is coming into picture. So here we will talk about this neuromorphic computing for AI-enabled hardware-based Hopfield neural network. Under this category, we will talk about neuromorphic computing and the Hopfield neural network and its architecture, how it is designed for this case. So why this neuromorphic computing is coming into picture? Though we have a very strong technique is present that is called the deep neural network is associated with us, which can able to perform a classification, the similar that means a better perform the classification in a better way and provides a very high accuracy. But still people are looking into this neuromorphic computing. Why? What is the necessity of behind this? That we should understand, so that we can understand that what exactly this neuromorphic computing and how it is related with this neural network. So as already we know that the computers we are using for all kinds of applications like communication, engineering, computing, classification, regression, etc., etc. If we look into the power consumption in these computers, then we can see that nearly 5 to 15% of the world energy is consumed during the process of data manipulation, translation, that is called transmission, processing, storing, etc., etc. So in 1990, researchers thought of how to reduce the power of this computing. So they have tried to develop one technique that is called neuromorphic computing. Researchers have developed one technique that is neuromorphic computing, and this neuromorphic computing inspired by our human brain. That is, the nervous system inspired analog computing devices are power efficient, and conventional computing devices fail in case of speech as well as image processing. So for that reason, people are using CMOS technology system for power efficient devices. But in parallel computing, CPU counts up to millions in case of supercomputers, multiprocessor, etc. In case of machine learning, deep learning, or in case of huge computation is required. Machine learning requires a very large amount of databases as well as noisy datasets. Deep learning requires a branch of machine learning based on deep layer architectures, which also requires more computations as well as more power. So that means if we look into the machine learning, deep learning concepts, all requires a huge computation or requirement of huge computation is involved in this case. So why this neuromorphic computing is coming? So neuromorphic computing is coming into picture to overcome the difficulty of power handling. So how this we can make a reduction of power? This neuromorphic computing was coined by this IBM research group, which is a biologically inspired chip. Basically, one of the best examples is called the True Knot. It implements 1 million spiking neurons, 256 million synapses on a chip with a 5.5 billion transistors with a typical power drawing capacity of 70 milliwatt. And the size is scale up to a human brain that is equal to consume 10,000 times more power. So that means if we scale up the size to a human brain of this combination, that is 256 million synapses on a chip with 5.5 billion transistors with a typical power of 70 milliwatts, and all combined to a size of a human brain, it will require 10,000 times of more power. So people are thinking of improving this CMOS and in a computer hardware to overcome this difficulty. So there is a concept of coming neuromorphic computing, and the results of why we are going for this neuromorphic computing is that the reason behind is that the atomic limit cannot be miniaturized beyond certain limit. Local energy dissipation limits the device packing density. Overall energy consumption is too high. So these are the problems, these are the reasons for which we are going for this neuromorphic computing. So why there is a need for enhanced computing? Already you know that much lower power consumption than the conventional processors. This neuromorphic computing is used. So this neuromorphic computing supports dynamic learning in case of complex and as well as unstructured data. It replaces existing numerical methods where low power function approaches are used. So these are the reasons why people are going for this neuromorphic computing, for this deep learning or the machine learning. So if we look into the architectures, that is the von Neumann architecture, basically this is nothing but a core concept architecture. It is divided into several major physical rigid functional units or components, such as memory unit, ALU, that is the arithmetic and logic unit, CPU, central processing unit, data path, etc. So the limitations present in von Neumann architecture is that there is separations present in case of different units. They are physically separated. That means separation produces a temporal and energetic bottleneck in case of a von Neumann architecture. So this bottleneck limits the future development of the revolutionary computational systems and increases aggregate computing performance, but basic computing elements are the same. So in contrast to the von Neumann architecture, this brain, human brain, has the advantages because it is energy efficient, is superior. Memory and processor in the brain are co-located because the constants have the different roles depending upon the different kind of learning process. So brain is a flexible system. So I can say that the brain can adapt complex environments. It is self-programming. It is complex processing. So the computational system is similar to the brain beyond the scope of this today's engineering. Still, people are doing the research on this neuromorphic computing. So this neuromorphic architectures, if we look into the neuromorphic architecture, the various computational elements are mixed together and the system is dynamic based on the learning process. So the dynamic process, various elements of a system change and readjust depending on the type of the stimuli direction. So here there is a comparison of this von Neumann architecture as well as the neuromorphic computing. If we look into the von Neumann architecture, we have one input device, one output device, and we have the central processing unit, which is consists of the control unit, arithmetic and logic unit, memory unit, etc. If we look into the neuromorphic architecture, this neuromorphic architecture is mimicking our human brain. So in this case, the address event representation inputs, that is known as the dendrites. Address event representation inputs, that is this is also the dendrites. This is connected with a short-term plasticity synapse. We'll talk about this, what is short-term plasticity synapse, long-term plasticity synapse array, and this is get connected with a synapse demultiplexer, some soma array, and this will give rise to the address event representation output, that is known as the axons. So these are the two differences that we can see in case of von Neumann architecture and neuromorphic architecture. And this neuromorphic architecture is popularly designed or used for this machine learning application to handle the huge amount of data as well as to make the network to be power efficient. If we look into this von Neumann architecture as well as the neuromorphic architecture, the von Neumann architecture, which consists of transistors, resistors, capacitors, inductors, and some communication circuits. So whereas if we look into the neuromorphic architecture, which is nothing but brain is based on a large collection of neurons, such as the body, synapse, axon, dendrites. So these are the nothing but the components of this neuromorphic architecture. In case of von Neumann architecture, the device has a unique characteristic, that is speed, size, operation length, etc. And there is a limited by the energy consumption, rigid design and functionality, inability to tolerate faults, and limited connectivity. So these are some points related to the von Neumann architecture. Whereas the neuromorphic architecture, if you look into the different components like a body, synapse, axon, dendrites, and these are adaptable and they have the fault tolerant capability. This neuromorphic architecture is more complex in nature. And if we represent the graphical representation of this von Neumann architecture as neuromorphic architecture, we can able to see the differences between the von Neumann architecture as well as neuromorphic architecture. In von Neumann architecture, it is represented by the transistor, capacitor, inductor, and some connections. Whereas neuromorphic architecture, it consists of dendrites, soma, axons, and they are interconnected, which is a similar structure to that of the human brain. So this von Neumann architecture, as an individual component, the silicon system show enhanced performances, but the system as a whole has a reduced functionality. But the neuromorphic architecture, the energy dissipation is smaller and speed is also smaller in this case. So if we summarize the differences of the performances in case of a biological neuron as well as the neuron equivalent, which is made up of the CMOS technology, then we can summarize the differences of the biological neuron as well as the silicon in terms of speed, size, voltage, neuron density, reliability, synaptic error rate, fan-out dimension, synaptic off energy, total energy, temperature, noise effect, etc. So if we look into the speed of the biological neuron, so it is of 1 millisecond, whereas the silicon has a speed of 1 nanosecond. So that means if we look into the speed of this silicon-based neuron, it is very, very faster. If we look into the size of the biological neuron, it is 1 micrometer, whereas the silicon neuron is almost 10 nanometer. If we look into the voltages, the voltage consumed by a biological neuron, that is equal to 0.1 volt, but whereas the silicon developed neuron, it is almost equal to 1 volt. So if we look into the difference of the voltages, then we can see that the biological neuron requires less amount of voltage, neuron density. So in case of biological neuron, this is 100,000 in mm square, whereas in case of silicon-based neuron, it is 5K per mm square. The reliability in case of biological neuron, this is 80%, and in case of silicon, this is less than 99.9%. The synaptic error rate, it is 75% in case of biology and neuron, and it is silicon-based, it is nearly about 0%. Fan-out, if you look into the fan-out of the biological neuron, it is almost 10 to the power 3 to the 10 to the power 4, which is a very huge quantity or huge amount, a huge number. So in case of silicon-based, it is 3 to 4. So that means this biological neuron is found to be more advantageous compared to the silicon-based neuron. Dimensions, that is equal to pseudo 3D dimensions. And in case of silicon, that is pseudo 3 dimensions. Synaptic off energy, that is 2 femtojoules, whereas this is equal to 10 picojoules. Total energy consumption in case of biological neurons is very, very small. That is 10 watts, whereas in case of silicon-based neurons, it is nearly about 10 to the power 3 watts. So the temperature is working, that is equal to of the biological neuron, that is 36 to 30 degrees centigrade. While the silicon-based neurons is working at a 5 degrees centigrade to 60 degrees centigrade. Noise effect, this is stochastic resonance, and this is very bad. The criticality, that is the age and power. So what we understood from the comparison of the differences of the performances of the biological neuron versus the neuron equivalent built from a CMOS technology. So we can see that the differences are very large. Scientific concepts are needed, including the system architecture. Silicon device exhibit a better computational capability or capacity for this case. So silicon device exhibit better computational capability, but it's a fault tolerance, energy consumption, ability to deal with the large data set is poor compared to the biological brains. Building a computational or conventional system relies on the ability to produce billions of highly controlled devices that respond in the same way to a defined stimulus. So if we look into the existing neuromorphic systems developed till today, so range of the computing architecture supports some form of neuromorphic computing optimized for mathematical approximation of a neural network. Artificial neural networks support fast matrix operations. Neural network architecture beats the general purpose CPUs in power efficiency by discarding the features not needed by the neural network. So true knot is one of the best examples. The true knot system requires 10 times as many transistors compared to the analog equivalent for the programmable SOMA, but not support the deep learning. Power difference between the analog and the digital implementations are also significant. Analogs are being efficient. So there are two approaches are there. Systems should improve the power like a brain. So performance need to reach like the brain. So for that reason, the neuromorphic processors have been developed. So which consist of 256 neurons, consist of 65,000 to 256,000 synapses. One of the example is called the IBM's True Knot, which is developed in 2015 and consists of 1 million neurons, 256 million synapses, and synapses devices based on the principle of memory stores, not by the CMOS. Next is the spin-car hybrid CPU neuron. This is developed by the University of Manchester, consists of 65,000 to 256,000 synapses. Facets. This is a wafer scale neuromorphic hardware system developed by University of Heidelberg, consists of 180,000 neurons and 4 into 10 to the power 7 synapses per wafer, supports 10,000 synapses per neuron. So these are the different comparisons of the neuromorphic devices that I have still developed. So the project names is mentioned: programmable structure, compact complexity, on chip, and what are the materials people are used for this. If you look into Darwin, this is nothing but neurons and synapses are the structuring, the programmable structures. On-chip learning is possible in this case. It is packed with the existing CMOS processes. DANA, this is the neurons and synapses programmable structures. On-chip learning is possible in this case. It was developed by using the FPGA as well as the AICTE. True knot, it is has the programmable structure is the fixed synapse on off. It don't support on-chip learning. It is packed with CMOS processes. Neurogrid, the programmable structure is fixed, that is synapses. Doesn't support on-chip learning and packed with existing CMOS processes. Brain scale, the programmable structures are neurons and synapse. It supports the on-chip learning and the materials that is used are wafer scale active. Spin the programmable structures are neurons and synapse, and this supports the on-chip learning. And this is the materials used as ARM boards, custom interconnections, etc. So if we will look into the architecture pattern of the neuromorphic hardware, basically we have to arrange the synapses in a dense crossbar configuration with a separate blocks of logic to implement the learning in a synapse and integrate and fire the SOMA. So during this process, we are facing some challenges. That is the fan-on, fan-out ratios of the crossbar. Real biological neurons have 20,000 synapses connection per neuron. Neuromorphic chips has 256 synapses connection per neuron. Whereas if you look into the biological neuron, it has a high number of synapses compared to the neuromorphic chips. So how to overcome these challenges? This is the diagram is given for the neuromorphic computing. We'll see once again for this case. So in this case, in case of neuromorphic computing, we are facing the difficulty of privacy and security, user authentication, network, device data monitoring, and end-to-end authentication. So how we can implement these needs? I hope it will be over by 12:45. Am I right, Mara? Should we any questions from the audience, or proceed till 12:45. Am I audible?
Dear participants, if you have any questions, you can unmute and then you can ask the question, please. Dear participants, if you have any questions, you can ask now. I think we're not getting any questions,
Okay.
Malaya Kumar
Okay.
sir. So shall we stop here?
We'll stop here. Can we? What time we have to start again?
At 2 o'clock, sir.
Can we start little early or
Okay,
okay,
shall we start at 1:45?
Yeah. If it will be start 1:45 so that I can finish little early.
Okay, sure.
If,
So we'll start the session at
participants
1:45 p.m.
Okay, sir. Okay, thank you.
Right, sir. Thank you. Sojana, take the proceedings, ma.
Yes, sir. So thank you very much, sir, Dr. Malaya Kumar Nath, sir. That's a wonderful session of this forenoon. So this is the end of the forenoon session. In the afternoon, we'll be starting at 1:45. So sir will be continuing in the afternoon session from 1:45.
Yeah, thank you, madam.
So dear attendees, you can go for a lunch break and the second half session will start at 1:45 sharp.